start this lecture 11 from this thought process which was lurking in my mind. It is important to teach pupils to learn by creating chain of curiosities rather than teaching a mere lesson, which is very important according to me, because I believe each individual is a learner and teacher by default. So, let us recall that what really we learned in the last lecture. We started the discussion with a quasi one dimensional flow. Quasi one dimensional flow means where there will be change in area, and you know very well that most of the our propulsive ducts, particularly nozzle and air intake, will be having varying area torque, right. So, therefore, we need to look at it very carefully and learn how to analyze them, not only the air intake and the nozzle, but also the in case of a turbine and compressor, we will be using some of these analysis as well. And for that purpose, what we did? We invoke the conservation of mass, momentum and energy equation along with equation of state for a perfect gas or an ideal gas. Then we combine together and derive a relationship between what? Area ratio and Mach number. Then what is this area ratio? Area ratio is basically any local area divided by critical area, right, and which is a function of Mach number and also the gamma, that is Cp by Cv. And we will use these equations and apply for what you call nozzle flow, because nozzle flow is quite important, is being used in the exhaust stream of a turbojet engine and also the rocket engines. For doing what? For producing the thrust, which is the basic requirement of a propulsive device or a engine, right. And if you look at the exhaust thrust can be broadly divided into two categories. One is the convergent nozzle and other is your convergent divergent nozzle. In convergent nozzle, what is happening here, which I have shown in this, there is a decrease in area, and this we can use only when the flow is subsonic, right. And we will dwell upon it and see that why we can't use it for supersonic flow, right. And there is a convergent divergent nozzle. If you look at, this is your convergent portion and this is your divergent portion, and this is known as the throat. That is the minimum area where the sonic or the flow will be sonic, or unity Mach number will be existing. Will it be existing all the time, or under certain condition it will be there? So, this convergent nozzle is being used in a jet engine in which is being shown in this figure. You can recognize this is a basically a combustor, and this is nothing but a turbine. That means, from the combustor the hot gas at high pressure passes through the turbine, gets expanded and it is further expanded in a convergent nozzle, right, and which is basically to produce the thrust. In most of the jet engines, right, except maybe turbo prop, where the nozzle is being used to produce the thrust. And so also in the ramjet engine and in the rocket engines. But can I use this convergent type nozzle for the ramjet engine, rocket engines? Can I use? Certainly no, and we will see why it is little later on. Let us look at convergent nozzle and learn how to analyze, how to understand what is happening inside the convergent nozzle by invoking the analysis which we discussed in the last lecture. For that purpose, let us consider a what you call convergent nozzle. Keep in mind that A2 is less than A1. That means, the area cross section at station 2 is less than the area at cross section 1. And of course, the flow is coming from upstream, and when it is passing through this convergent nozzle, there is an increase in pressure. Is it there will be an increase in pressure? Certainly no, there will be increase in velocity, right. If I want to increase in pressure at the exit of a converging duct, so what I will have to do? Is it possible I can get a increase in pressure for a converging duct? It is possible, provided the flow is supersonic. So, let us and to discuss it further, we will invoke a relationship what we have derived in the last lecture, that is d A by A is equal to m square minus 1 into d V by V. That means, if there is a decrease in this cross sectional area, that is means A2 is less than A1, right. That means, A2 minus A1, what it will be? If it is A2 by A2 less than A1, that means, this will be a negative, right. That means, d A, this is basically d A, d U A will be negative, right, provided if A2 is less than A1. If this is a negative quantity and if m is subsonic, that means, m is less than 1. So, then this also will be a negative quantities, this portion will be a negative quantities, and then what will be d V? V2 should be greater than V1, because left hand side is negative, right hand side is also negative. So, naturally V2 should be greater than V1. So, which you are saying, that means, if there is a decrease in area, V will increase, right. But if it is other way around, that means, area is increasing, that means, it is a diverging duct, then velocity will decrease. It will be act like a diffuser or a air intake, where there will be decrease in velocity and of course, increase in static pressure. So, let us look at what is really happening by putting this a convergent nozzle, this is a convergent nozzle and to a reservoir. As I told, reservoir means it is a very big supplier of the air, big large size tank, you can consider it, right, where the velocity will be 0, means that means amount of air is so much such that if a small amount of air is passing through this nozzle, right, then there is no change in the pressure and temperature in this reservoir. That means, P T is constant, that means, total pressure remain constant and total temperature also remain constant. Then only we can call it as a reservoir. That means, if you look at, if I take this A E is the exit, right, and if I take this area, it will be ideally A by A E right. If I say this A by A E, if I say this is my exit, will be tending towards what? Infinity, then only it is possible, otherwise not possible, right. By simple applying the your continuity equation one can think about, right. So, now let us say that I can because here in the reservoir the total pressure which is remaining constant during the operation, and if I will keep this pressure, right, exit pressure, right, or maybe little away from the exit, that we call it as a back pressure, right, same as that of the total pressure, what will happen? If somehow by some means I am keeping the downstream of this nozzle, because this is the nozzle, right, and what is this nozzle? This is a convergent nozzle, and I am keeping the pressure P t at this point, right, same as that of the P t. So, what will happen? There will not be any flow, and what will happen to the pressure here in these locations along the x direction? If you look at this x direction, what will happen to in this direction? If I take, it will be remaining constant, right. That means, if I am talking about this A, where the P v is same as that of the P t, then there will not be any flow, because there is no pressure gradient. And if this P v is smaller than the P t by a small amount, right, or is less than P v is less than the P t by a smaller amount, then what will happen? Then there will be a flow over here, right. But what will happen to the pressure? At this point, each point pressure will be decreasing, that means pressure will be decreasing, right. If I decrease this P v, that is back pressure further, then what will happen? This again the pressure will be decreased, and which is lower than the previous case, right. But what happens to the velocity here? What happens to the mass flow at the exit of the nozzle? This is my nozzle exit. So, what happens to the my nozzle mass flow rate at the nozzle exit? Will it remain same, or it will be decreasing, or it will be increasing? What it will be? As my back pressure is decreasing, my mass flow rate will be increasing, because my velocity will be increasing and my static pressure also will be decreasing. So, if you look at, if I am here, there is no flow, that is corresponding to condition where back pressure is same as that of the total pressure in the reservoir, and when I go to the B, that is back pressure is lower than the reservoir pressure or the total pressure. Therefore, there is a increase in mass flow rate, if you look at mass flow rate here, right. And if I further decrease to the point C, there is a increase in mass flow rate and decrease the pressure along the x direction, right, in the nozzle. Is that clear? Now, if I will come to a point D, where it will give me the what you call the velocity, certain amount of velocity, certain amount of mass flow rate, and for which of course, this nozzle is being designed. You can call it as a P v is equal to the design pressure. But if I decrease this pressure further, let us say at the point E, what happens? There will not be any increase in mass flow rate, or there will not be any increase in velocity. Why it is happening? Under what condition it will happen? Can anybody tell me? That means, if there is no increase in the mass flow rate by decreasing the back pressure or the downstream pressure of the nozzle, we can call it is almost choked, or it is choked. That means, you cannot really increase the mass flow rate of the nozzle, whatever the pressure you apply. But why it is happening? Under what condition it can happen? If I further decrease it pressure, back pressure, maybe in anticipation that it may work for me, right, then still there will be no increase in mass flow rate. there will be no increase in mass flow rate. That means it is choked, whatever I am doing, even if I will go to the vacuum, the lowest pressure I can think of, I mean absolute vacuum, then I cannot really increase the mass flow rate. That means it is choked. Why it is happening? Why? Because at the exit it has reached the Mach number of 1. If it is reached, then it cannot really sense the any change in the back pressure, which will not sense. That means, the fluid element which will be in the reservoir on the upstream of this exit, it will not sense, look, there is a change in the pressure. So, that we will have to go, fluid elements should feel, okay, let me move. They cannot. Why it is so? What I had talked about earlier, it is because the speed of sound will be propagating. That means, the disturbances at the downstream, which is controlled by the back pressure, that is basically disturbance, right. It moves at the speed of sound, right. So, therefore, it cannot really know it is having, because these fluid are at stationary, right. So, therefore, it will not be, and we call it as a choked condition. That means, this is my choked condition, this is the choked point. And what pressure it will come at, that we will see little later on, maybe next, right. And I want to increase the mass flow rate. What are the ways and means of increasing the mass flow rate? I cannot do. Is there any way I can do it? Is it a requirement in propulsive devices where we need to increase the mass flow rate? For example, I am chasing a enemy by a fighter aircraft. So, I will have to increase the mass flow rate, and so also, otherwise I will be, I cannot manage, right. Suppose the pilot or the he wants to go at a very high speed and it is choked, then what he will do? You may say that he can add more fuel, right. Is it possible? Why not? You are having afterburner, you can put more amount of fuel, more energy, right. Can you increase the thrust? Because like thrust I will be discussing little later on, but as you all of you know that thrust will be proportional to the exit velocity. I cannot increase exit velocity, it is choked. So, therefore, I cannot manage, right. Is it so? Actually, it is not. That means, there are several ways of increasing the mass flow rate, also the velocity, right. Velocity of course not, but mass flow rate I can, right, if it is choked, like So, how I will increase the mass flow rate then? That is one question, and another question, can I use this concept in some other places as well, this choked condition, which is a problem. Can I use this as a solution for some problems? Because if you look at any problem comes to you, you should think it positively and see that what really I can learn, how I can use it to my advantage. That is the very important concept in life. So, also in fluid mechanics. So, if you look at, let us look at the expression what we had derived in the last lecture, that is m dot A divided by A is equal to m, this is the what you call Mach number, root over gamma P t and root over R T t, and into in the bracket 2 divided by 2 plus gamma minus 1 m square power to this gamma plus 1 divided by 2 gamma minus 1. This we have already seen. What it is indicating? That means, this mass flux per unit area, right, will be proportional to what? Proportional to the P t. It is inversely proportional to root T t, and of course, the gamma and Mach number, right. From this, can I learn something looking at this expression? That means, whatever the question I ask, when I look at this expression, I can get the answer. What are those answers? Can anybody tell me? I want to increase or change my mass flow rate, rather increase the mass flow rate when it is choked. So, what are the ways to do? Can you look at and tell me this expression? That means increase the total pressure, right, or what else I can do? Decrease the total temperature, the reservoir temperature, right. There is another way. Mach number is a problem, na? See, because the exit Mach number becomes 1, it is choked. So, therefore, I cannot have a control over the exit Mach number, right. It is not a flying, it is not an aircraft which is flying, we are talking about engine in the nozzle, right. What else? It is there. Gamma is a fluid, if I am using air, it is air. I cannot change in the in an aircraft, can I change, right. And even if I will change, what by what percentage, that is also one question, right. It is quite difficult in practically change that. Exactly, the area, right. That means, if I change my area, I can do that. So, let us look at whether we use, like as I told, the particular conversion nozzle chokes at a particular back pressure, right. And if variable area nozzle is used, choking can be delayed to a desired back pressure. Convergent nozzles with variable area system are used in fighter aircraft engines. Why? To have a higher thrust, particularly when you are using the afterburner, right. So, what is being used in real practical situation, that you vary the area, right. A series of how we can vary, of course, there are several ways of doing it. This is one of them. A series of pie shaped segments are used to construct a variable area nozzle, which is shown here. If you look at, in this case, this is all together, right. This is a lower area, exit area, right. If you look at the velocity here, is coming out, this is the exit area, right. And when it is at maximum, like when you need, we can increase this area, right. Right. This is your also exit area of the nozzle, right. So, therefore, by just simple technology, like you can just increase it, decrease it, collapsible, it is kind of collapsible like nozzle. You have seen that collapsible gate, you can increase it, decrease it like that. Some mechanism has to be. Of course, there is a lot more work has to be done, because similar thing cannot be really done for the convergent diversion nozzle. Is it really true, I am saying, or is there a technology available by which you can also change that area? We will think about it. Let us now look at convergent divergent nozzle, right. And as I told you, that in case of a convergent nozzle, my exit Mach number cannot really go beyond 1, because it is choked, right. That means, I cannot really use that convergent nozzle when I want my exhaust velocity should be greater than 1, right. If I want that, then I cannot really use convergent nozzle. So, therefore, I need to have a convergent divergent nozzle, right. So, as I already have mentioned, that main purpose of a nozzle is to expand high pressure hot gas to have a high jet velocity, much greater than the sonic speed at the exit in case of a convergent nozzle, right. So, therefore, we need to go for a convergent divergent nozzle. So, if you look at typical convergent divergent nozzle is shown here, which is having a convergent section, having a throat section, right, and this is having a divergent section. Of course, the hot gases will be coming from the combustion chamber, particularly in case of a rocket engine, whereas this nozzle, convergent divergent nozzle, when I am using in case of a ramjet engine, it will be also coming from a combustion chamber. But when I am using in a fighter aircraft, of course, rarely it is being used, right, then it will be coming from a turbine, right. The gases, hot gases will be coming from turbine. So, Now, this convergent divergent nozzle, it is known as also D-level nozzle, right, because it is the after the person who really came up with this convergent divergent nozzle. You know, like, did this nozzle was first, whether this nozzle was first designed for an aircraft engine? What for it was designed? Any idea? It was really designed for the steam engine, okay. Not related to the air, but it is profusely used in case of aero applications and other places as well. So, now coming back to this, what really happens, we will be looking at this isentropic analysis, or the analysis carried out for a isentropic flow, which will be invoking. And if you look at the flow is taking place over here, and this is the throat where the Mach number 1 is occurring, right. And if I look at the pressure, right, along this CD nozzle, right, this is a CD nozzle, right. What is happening? If you look at the pressure, pressure decreases because the fluid or the air will be increasing. If you look at the Mach number increases here, and then beyond this divergent portion, it again increases further, because the throat, it is already at the sonic condition, and this is the diverging portion, right. So, therefore, it increases further, and this portion is the supersonic region, this portion is the supersonic region, supersonic flow, and this is subsonic. And keep in mind that temperature also decreases due to expansion of the gas, right. So, let us look at a convergent divergent nozzle, particularly invoking the isentropic analysis, and we will consider the nozzle being connected to a reservoir where the total pressure remains constant. In this case, the A by AT is tending towards infinity, right. That means, area of the reservoir, cross sectional area of the reservoir is much larger than the throat area. This is your throat area, right. And it is designed for certain Mach number, that is MD I can call, right. For certain Mach number, this area ratio, if you look at, this is my exit area, right, and this is my inlet and throat area, this one. So, it is designed for certain what to call design Mach number, right, velocities. And if this back pressure is same as that of the PT, there will not be any flow, as we have already discussed in case of a convergent nozzle, because there will not be any flow as such, because there is no pressure gradient. Now, if this back pressure is lower than the PT, then there will be flow. If there is a flow, then what is happening here along from the inlet, this is your inlet, right, and from the flow is taking place, then what is happening to the pressure along the x direction, or at the center line, you can say center line of the nozzle. What happens to the pressure? Pressure will decrease, but then when it comes over here in the divergent portion, like this is your divergent portion, what happens to the pressure? That means, the pressure will decrease in the convergent portion. This is your convergent portion, decreases till this, and then again it will increases, because if the flow is subsonic in this region current, right. That means, of course, at the reservoir P by PT will be 1, this is at the reservoir. Okay. Then after that it decreases and reach certain value at the throat. If you look at this is the throat kind of things, right, and then of course, it again increases depending upon how far the PV less than the PT. Here we are seeing it is very small as compared to the article. It is change from the PT by infinitesimally small. Then if we decrease it further, this back pressure I decrease it further, what happens? It again follows the same path, and that means pressure decreases and again increases further in the divergent portion, right. And if that means at this point throat, what is happening? The velocity or the Mach number is increasing. What happened to the mass flow rate then? Mass flow rate also increasing at the exit of the nozzle, but what happens to mass flow rate at the throat? What happens to mass flow rate at the inlet? Is it same or different? Naturally, it will be same, and then it is all increasing when I am decreasing the back pressure, right. So, if I will go on decreasing this back pressure and reach a condition where the Mach number at the throat will be equal to 1, right. That means, the pressure is decreasing in the convergent portion, and then it is again increasing, right. So, this condition, that means what is happening? The throat is choked, right. Throat is choked. If I decrease the back pressure further, what happens? What happens to the mass flow rate? Okay, what will happen to mass flow rate? It will remain constant. It cannot really increase beyond that, because why? If you look at the Mach number has reached 1 here, I mean this is the plot Mach number versus x, right. Keep in mind that this is also the same x along the x direction. So, that means this point is changing, right. This is the throat region basically, right. And then if I decrease it further, what happens? Any idea? Suppose I am here something, some other region, what will happen? PV 3 instead of PV 3, I am PV 4, right, because this is basically come over here, right. What will happen? We will discuss, yes, it cannot, no, because if I decrease, there is a the mass flow, there will not be any increase in mass flow will be remaining constant, right. For example, okay, we will maybe discuss little later on, but if it is designed for certain Mach number, right, that means it will be having certain exit pressure or the back pressure, right. If I am applying the same back pressure here, that means PV is equal to PD, right. What happens? It comes over, that means the pressure decreases and reach the design value, right. And if you look at this P by PT, what is this relation? This is meant for only isentropic flow, right. That means, if my back pressure happens to be same as the design pressure, right, for which it is designed, that means the same exit Mach number, right, then the pressure will be like that, but in between what happens? If I decreasing in between this pressure, what happens? There will be a suck formation. Why it is so is a thing to be ponder about, and we will be discussing about sucks little later on. Okay. Now, what happens to the Mach number here? That means, it is also reaching the design Mach number whenever it is back pressure is same as that of the design pressure at the exit of nozzle, right. But as I told that what is happening in the mass flow rate, if I go for this this line, if I goes on decreasing the back pressure, the mass flow rate will be increasing till it reaches the Mach number 1 at the throat, and mass flow rate will be remaining constant, although I will go on decreasing further. That means, in this region mass flow rate will be what? Will be remaining constant, although the back pressure is much lower than the critical back pressure. If you look at this critical back pressure is basically equal to, this is I call critical point, or choked point, right, and this is equal to P is equal to 0.528 P T, that is critical, right, and sometimes we use as a star, P star. This is because of choked condition or the sonic flow, right. I mean, that will tell you where it is choked, right. If my P pressure at the throat is equal to the 0.528 P T, then it is. Keep in mind that this is possible only for the an isentropic flow, right. When isentropic is occur, like due to heat addition or due to other dissipative effect like boundary layers and other things, this will not hold good. Okay. Keep in mind that. So, now if I want to increase or decrease this mass flow rate, what I will have to do? If I want to increase the mass flow rate from this level to that level, then I will have to increase the P T of the reservoir or the total pressure, or decrease the total temperature, or both. That means, one I will be increasing and other will be decreasing, that way combination of both, right. Similarly, I can decrease this what you call pressure, total pressure, and total temp and what you call increase the total temperature, or combination of both for decreasing the mass flow rate in a nozzle, right. So, this is the things which we need to keep in mind, and the question what I had asked, that how to really increase this area in case of a convergent diversion nozzle is a design challenge. It is quite challenging, right. How we will do that? Mechanically, right. Of course, people have done it, and you can look at it as we go along. We will be discussing if I will get some time. So, now let us look at an example. A convergent diversion nozzle is to be designed for Mach number 2, right. Air is entering from a tank, that is basically reservoir, at pressure of 1 megapascal, temperature of 298 Kelvin. If exit diameter of the nozzle is 100 mm, then we will have to determine the throat area and exit area ratio, right. That means, throat and exit area ratio, AE by AT we need to find out, and maximum mass flow rate it can handle, right. So, let us look at our diagrams what we have already seen. We need to find out basically to find out these are the given ME exit is equal to 2, that is Mach number. D here at the exit D basically is given as 200 mm, 100 mm, and P T is given as 1 megapascal, T T is given as 298 Kelvin. So, we need to find out basically throat exit area, that is A by A star or is equal to A by A T, this is throat area, and we will have to find out m dot maximum, right, to find. So, for that what we will have to do? Very simple, because we know the Mach number here m e, right. If I know the Mach number, I can, and it is a air. So, gamma is equal to 1.4 I can use for air. So, if I will invoke this expression, right, and which we know A by A star is equal to 1 by m into 2 by gamma plus 1 into 1 plus gamma minus 1 divided by 2 m square power to the gamma plus 1 divided by 2 gamma minus 1. See, gamma is known, m is known. So, you can evaluate here what it would be. This is basically is equal to A by A t. That means, this is basically A by A t, right. And if you substitute these values, you will get 1.69. That means, it is a very direct one, right. But you need to remember this formula, right. But there is another way we can get these values from a table, because right we can really use the isentropic table. Let us look at a typical isentropic table for gamma is 1.4. What will be given? This is your Mach number T t by T, and this T t is total temperature divided by T, right, which already we know the formula, right. T t by T is equal to 1 plus gamma minus 1 divided by 2 m square, right, and P t by P we already know, that you can use directly, or you can use this table rho t by rho and A by A star. Already the expression I have used to evaluate in that example, and this is mass flow parameters, which already we have discussed, that is 1.9. And what you can observe from this table? Can you observe something from this table? When the Mach number is increasing, that means 0.1, you will see the temperature ratio T t by T is almost equal to 1. But if it is Mach number became 1, what happens to the T t by T? 1.2. You cannot really neglect the effect of Mach number when the Mach number is very high, right, that which I have already discussed. Similarly, P t by P is 1.89, this is 1.007. Similarly, for the density, and what happens to area? Area becomes 1 at sonic condition. Mach number 1 is equal to 1, basically sonic. So, area ratio will be minimum, that is the A by A t or A star is equal to 1. Of course, the mass flux is becomes the mho kind of things. And of course, when the Mach number becomes 2, it is the T t by T becomes higher. So, also other quantity, and also the A by A star becomes very higher than the 1. If you look at when the Mach number less than 1, that is 0.1, it is very high, here it is also high. But let us the another data which I have shown here, that is 2.2, and others that is like T t by T, P t by P, rho t by rho, and other things are given in this table. Now, suppose in your example it is given that your Mach number is 2.1, that means this data is given and this data is given. I want to evaluate using the table, what I will have to do? You will have to do a linear interpolation between the data. That means, you are assuming it to be linear. Is it really the relationships are linear? Certainly no, you have seen those expressions is a nonlinear in nature, but however we do it for the simplicity, and it incurs certain errors, and that errors is very less, can be tolerable, provided the interval between two data are small. So, that means, we are in the 2. So, therefore, the area ratio if you look at what it is 1.68. We will use this thing, and this area ratio become 1.68 if you look at, and if you look at 1.69 and 1.6, there is an error, but of course, it can be tolerable. You can use either the table or the equations, but equations will be correct one, or it will be more closer to that, or it is better to use equations, right, when you want to have a error free data kind of things. But however, for the quickness you can use the table. Now, the area I can calculate that is 5 by 2 d, and then we will have to get this is a small area like which is having, we will just substitute values and get that. So, then A t is nothing but is equal to A star, and you can get this is a quite a small as compared to the A exit area, because this A is same as that of the exit area. It can be any other place as well depending upon the Mach number. That means, this expression what I am saying, right, it can be applied any cross section, right. And then in the mass flow rate, m dot max, if you look at, is equal to A star P t root over gamma divided by root over R t 2 divided by gamma plus 1 power to the gamma plus 1 into 2 power to the gamma minus 1. I will just substitute these values. Already I have evaluated A t. You might be wondering why I was doing that, is basically I want to find out maximum mass flow rate through the nozzle. So, therefore, I need to evaluate this A star or A t throat area, and P t already I know this is 1 megapascal, and T t I know. So, I will substitute these values and get that expression m dot max is equal to root over, you can see that it happens to be 10.9 kg per second. So, basically we are using this isentropic relationship to get various values kind of thing. Now, question arises, why we need to go for table? If you look at this expression, right, suppose in case I know the Mach number, right, or let us say I do not know the Mach number, but I know the area ratio. How can I find out Mach number? Is it possible? So, for example, in this, there is another example or another problem where A by A t is given, but I need to find out Mach number. So, how I will get? Can I get? Right? Yes, numerically you can get, right, or there is an approximate solutions or approximate equations will be there, expression which you can get. That means, I can express this Mach number in terms of A by A t, right. That is again approximation. So, therefore, we need to go for a table where I can use those values, because I can put various Mach numbers and then give A by A t and then other P by P t and other things are right, and then I can use it. So, that is the one way of solving this, unless otherwise of course, computer is not at your hand. In earlier days particularly, where computation was not that easy to do. So, people were using this isentropic. Therefore, there is a importance for using the isentropic table or looking at the isentropic table. Okay. With this, I will stop over, right, and then we will see in the next lecture about the sock and how to handle normal and oblique sock. Okay. Thank you.